everyone. Good to see you all again. Thank you very much for having me. So Lee, I met Lee in 2010, and I was inspired by Lee. So I'm a neurologist myself, and I've been basically going into medicine with the love of the brain, but realizing very quickly when you start practicing neurology, and I had some personal experiences myself, that despite being one of the largest problems, I think neurological disease causes the largest amount of disability. In terms of medicine, and this culture's changing now, it was always the field where you could diagnose everything but treat very little. And so I first saw, what you just saw Dr. Hochberg present is really the foundational layer. Now there were people that came, I mean, John Donohue's in the audience, there were people that came before, Miguel Nicolelis as an example. There are many people who came before that have laid the groundwork here, but Dr. Hochberg's work from BrainGate took this into the clinical domain, but we're still here in 2024 and we haven't yet seen what's required to move into clinical translation. And so we've only got a small amount of time, and I wanted to briefly speak about the concept behind the company that I started almost over 10 years ago, because the same idea holds true, which I think is going to be one of the major unlocks for getting this technology out to a lot of people. And so that concept is basically this idea that happened in medicine before. And if you look back, so when I started in neurology, one of my best friends in Australia, Rahul Sharma, he loved cardiology, and he wanted to go and do interventional cardiology, which is one of the sexiest areas in medicine. It pays well, it's like very fast moving, there's lots of technology, and it's a rapid growth area. You probably all know someone who's had a stent. You now can deliver a range of technologies into the heart that don't require open chest surgery. And so Rahul told me a lot about what happened in that field, what happened over a 20 or 30-year period to make this one of the most exciting areas in medicine. And when I looked back, and there's a lot of work that went behind this graph, and this tells a big story. And the story is, how did this field go from kind of where, so Lee used the term implantable neurotechnology. So I think there's a concept here that if you can get into the brain, there is huge potential for a range of problems to be solved. But you've got to get into the brain, and you've got to do that in a way that can scale if you want to have the huge amount of impact. And if you want to have the biggest amount of impact in medicine, you want to try and achieve what happened before in a field like interventional cardiology. So I went back, and over the years, I've been doing a lot of reading and understanding about this. And I read about this guy called Andreas Grunsig. So Grunsig was a cardiologist back in the time when there were just several 100,000 of heart procedures happening. And that's kind of where we are with the brain right now. Because back then you had to crack open the chest to get to the heart. Think of bypass graft surgery. No one has that anymore. It's stents now. What Grunsig did, he was one of the first people to figure out how to put balloons up in a blood vessel. And there's a story where they were already doing some ballooning in the legs down here and a little bit in the heart, but he said, no, if this is going to scale, we have to get out of the operating room, and it's okay to put a balloon up in your heart. So the Christmas party was happening at Emory Hospital, I think in Atlanta, in around 1981 or something. He went downstairs, took a nurse, locked himself in the basement, put a catheter in his own heart, blew up a balloon in his heart while awake with no anesthesia, and didn't die. And then he pulled it all out, went up to the Christmas party, and announced that he'd just done it. And he was a very flamboyant person, and it took off around the world, this story of this crazy cardiologist blowing up a balloon in his heart. The thing was, the technology already existed, but it was so important because he did it in a way to say, you can do this in an ambulatory setting, we can get out of the operating room and deliver the same technology without having to spend 6 hours in the operating room. So that then led off to a string of technological advancements: balloons, plasties, stents, then pacemakers, mapping and ablation, and now structural heart disease. So if there's something wrong with your heart, the chances are that you can go and get it fixed through a catheter in your wrist without having to crack your chest open. And it's now, there are not many fields in medicine where they're now in the millions of procedures per year. There's 1 million pacemakers, there's 1 million stents, and there's hundreds of thousands of others procedures. Neuro is still in this, so this is what it used to look like. Sorry, that's very gory, but it's real. Like, that's what had to happen if you needed a valve replacement, cardiac bypass graft, and now it all happens through this. And remember, the amount of cardiac problems is the same as the neuro. The heart and the brain are the two biggest disease causes in the body. We're still at this domain. This is a recent photo. This is a typical type of procedure that a neurosurgical resident performs. Neuralink's getting a lot of attention. It's on the basis of brain gate technology that Dr. Donohue and Hochberg have done. Deep brain stimulation has been around for a long time, but there are some really important lessons to be aware of here. The technology's got huge potential. Parkinson's disease, deep brain stimulation, that's also been around for 20 years. Still only 10,000 of them happening a year, despite being a huge problem and the technology working very well. Epilepsy's the same, tremor, OCD, and now implantable neurotechnology for BCI. Huge potential, but there is a challenge around scaling that technology if you're going to stay in the operating room. So the brain is always 30 years behind the heart in technology and medicine. And we've had our little Grundsig moment. Now, it's not quite as dramatic as what you just heard, but if you have a stroke now, a blood clot that goes up into your brain, you can now get a procedure that has a catheter that goes up to your brain and sucks out the clot like a vacuum. And if you do that within 6 hours, Manhattan's a great place to have a stroke because you're going to get treated very quickly, very high quality procedures. The reason that's important is because because it works so well, governments around the US are now mandating that these physicians that can do catheters up into the brain have to be available down at community level hospitals. And there's almost as many of these now as there are for cardiac cath labs. The difference between the heart and the brain is that, and it all started in the heart as well, it's a mechanical pump. The brain is not a pump. You've all seen incredible images of how the brain works and where we're going with this technology. So our whole vision from the beginning was, if we've solved the mechanical aspects of getting into the brain, we're now moving into a domain of achieving sensing or stimulating the brain, but without having to perform open brain surgery. And that's the foundational concept with Synchron. You've seen the high end of what BrainGate's achieving. We have a constraint with how much information we can get out of the brain with our first generation system, but I'm painting out a long pathway here where if we can solve these technology hurdles, we can get to that level of performance. And to commercialize this technology you've just seen, it's all about demonstrating the restoration of independence. So clinical translation and clinical trials means taking what you've just seen and then converting that into clinical trials where there's quantification of independence. And us, Neuralink, a lot of the other most groups are focusing on the ability to control devices that are widely available already. So we did our first human implant in Australia in 2019. This is what the device looks like now. It actually looks a lot like a pacemaker. You can see the cable coming up the blood vessel to the top of the brain, so that gives us a certain amount of access to a certain part of the brain. It's not as much as what we'd like, but that's a good starting point. And we then got our US approval. We started it. So that was published in JAMA Neurology last year, so the early safety and efficacy of this system. We're now about to finish our 10th 12-month follow-up of our 10th patient with this system, and we're now thinking ahead to the future with what a pivotal trial is going to look like for the patient population that you've just seen. We're excited. I think brain-computer interface was the starting point for Synchron, but we're looking at, and essentially what happened in cardiology was we looked at what technology can be delivered through open neurosurgery, and how can we deliver that through a blood vessel. And so BCI, what we're calling Sync, is our first product that's going to be coming into a pivotal trial next year, but we're really excited about 3 different products. A brain monitoring platform, which essentially uses the basis of a BCI as a stable amount of hardware that can stay in the brain, do analytics, and provide forecasting ability, kind of like a blood glucose monitor for a diabetic patient. A brain monitoring is a seizure prediction system for a patient with epilepsy. And we're really excited about deep brain stimulation. It's a technology, if you've seen it with anyone with Parkinson's disease, incredibly effective, very underpenetrated, very hard to access, very few centers in the country that can do it. We're going to deliver that in a way that can be scaled and make that available to a much larger number of patients. I'm determined to finish because last year I got pulled off stage and I've got 10 seconds left. And this is the last stage. So I think Neurotechnology, I think we're coming into a domain where this can go into the millions of procedures per year, but we're going to have to find ways to scale the delivery of the technology to patients, and that's what Synchron hopefully is going to figure out. Thank you very much. Thank you for having me.